Hello everyone. So in last video we have seen the voltage series feedback connection type. So this time we'll discuss the voltage shunt type arrangement. In this very arrangement we can clearly see that on both the terminals, I mean on output section as well as on the input side, both the connections are parallel. That means that feedback amplifier is basically connected in parallel at both the sides. And from our discussion in the previous videos, we know that if the connection is made parallel, it will definitely contribute to reduce the output impedance. And let's assume this to be ZOF. The output impedance is ZOF. Likewise, on input side, I'll assume ZIF to be the feedback input impedance. Now in this case, both the connections are parallel. So both the impedances means input impedance and output impedance, they both are going to decrease. In this network, the input is a current source and input value is an current Is, and output we are getting is the voltage V0. So let us start with the mathematical part. Again, we'll be calculating three things: the gain, number two is the input impedance, feedback impedance, then feedback output impedance. So let's begin. Now, if we have to calculate the gain of this whole network, it will be simply we can simply notice that V0 is the output value. So let's write V0, and what is the input here? Is. So output divided by input, that will be our gain value, and I'll represent it with A of F, the feedback gain. Now let us rewrite the equation by substituting a few things. AF will become equal to V0. V0 we can substitute with, we better know that V0 is nothing but the gain of amplifier multiplied with the input current value. So this becomes A multiply II. So I can write in place of V0, I'll write A multiply II over this Is I can replace as, see here we usually have a mixer circuit. Mixer actually performs this subtraction operation. Basically it is a negative feedback type. So II, which is the output of this mixer circuit, will be equal to Is, the source current, minus the feedback current value If, right? But this time I have to substitute for Is, so I can easily get this Is value from here. This will become II plus If, right? So let's put it here, II plus If. Now we better know that If is the output of your feedback amplifier, and what is the input value for this one? V0, right? So V0 will be the input and output is If. So If is basically the input voltage multiplied with the gain of the amplifier, that is beta. So it becomes beta V0. So we can again rewrite this equation as AII over II plus, in place of If we'll write beta V0. Now we already know the value of V0, so we can substitute it here. AF now will become equal to A multiply II over II plus beta. In place of V0, I'll substitute with AII, right? Now just take common the IA value from denominator. So II over II multiply 1 plus beta times A. Now this II in the numerator will get cancelled out with the II in the denominator, so that the gain finally reduces to, feedback gain finally reduces to A divided by 1 plus beta A, which is the same gain as we were getting for voltage series feedback amplifiers. So here we can notice that the gain value A is being reduced by a factor 1 plus beta A. Now let us move on to the effect of feedback on input and output impedances. Now let us assume ZIF be the input feedback impedance. Zi is the input impedance of transistor device, and Is the input current, and obviously it will develop a potential across this transistor device, so that we can write this thing mathematically. ZIF equals Vi over Is, right? Now we'll substitute Is in similar way as we were doing in last analysis. So Is will become equal to II plus If, correct? And obviously we know that If is nothing but beta times V0, so we can again rewrite this equation as ZIF equals VI over II plus, will in place of IF I'll write beta times V naught. Now let us multiply and divide by II. So ZIF will become equal to VI over II. In denominator it will become II over II plus beta V naught over II. Okay. And we know that Vi over Ii is nothing but equal to Zi, right? Likewise, V naught over Ii is equal to A, right? The gain of the amplifier, right? So I'll replace these values with Zi and A, and obviously the Ii will get cancelled out, right? So we are ultimately left with Zi in the numerator over 1 plus beta times, in place of V naught over II, I'll write A. So again, you can notice that the feedback input impedance is being reduced due to a parallel connection. That means whenever we have parallel connection type or shunt connection type, we'll observe a drop in the impedance value, and that drop will be by same amount, 1 plus beta A every time. Now let us move on to the effect on output impedance. Now let us assume output impedance, output feedback impedance to be ZOF. Now whenever we are supposed to calculate the output impedance of a network, we need to make its Thevenin equivalent. That means the first thing we'll do is will reduce all the independent sources to be equal to 0, and dependent sources will remain as it is. Like we can see over here, IS is an independent source, right? But AI is an dependent source which is being dependent on II. So definitely this IS will reduce to 0 and AII will play in the circuit. So we need to make this open circuit at the input side to make IS 0, right? Secondly, we need to put an open circuit across ZL, and obviously this ZL will replace with a potential of V naught, right? The same potential we are having previously. Now let us assume that V naught is contributing a current I naught which is flowing through Z naught, so that we can write this thing mathematically. ZOF, the output feedback impedance, will be V naught is the potential divided by I naught, and I naught we can easily calculate from here, as it is basically developed across Z naught, and at one end it is having a potential V naught, right? And at another end it is having a potential AII. So I can write it like V naught minus AII, and this is basically developed across Z naught, so I'll divide it by Z naught. Now as we are trying to obtain the output impedance parameter, so all the parameters in this equation I'll try to convert to output equations, output parameters. So let us try to replace this II with a few things. II generally is actually, it is the output of mixer, so it is we can write as IS minus IF. Now we know IS is already 0, so this will become equal to minus of IF, and from here actually it is the output of feedback amplifier, so we know the value, it is beta times V naught, so this will become minus beta times V naught. So we can substitute this II with minus beta times V naught. So let's do it. V naught minus, in place of II I'll write minus beta times, so this minus minus will become plus, multiply with beta times V naught divided by Z naught. In next step we'll just rearrange the equation, we'll write V naught, we'll take V naught common from numerator, and we'll write V naught over I naught. So this equation will become equal to Z naught divided by 1 plus beta times A. So you can clearly see that, and that is nothing but the output feedback impedance, right? So you can clearly see that on having a parallel connection on output side as well, the output impedance, output feedback impedance is being dropped or decreased by a factor 1 plus beta A, by amount 1 plus beta A, right? So similar type of analysis we'll try to do for remaining feedback amplifiers. So till then, thank you and have a nice day.